Okay, welcome to section 2.1. This is when we finally get a chance to do some calculus. In this particular section, we introduce the notion of the derivative. And what the derivative is another function. So we start with the function f of x, and using the tools of calculus, we are able to discover a different function, which we refer to as f prime of x. And the job of this new function is to simply reveal the slopes of tangent lines at any given x value. So instead of having to reuse the limit formula over and over and over again, we actually can use it just once, and we can reveal a new function, and that new function will just do the job. In other words, you say to this function, I'm currently at c equals 5, f prime of 5 will give me the slope. I'm now at c equals 7, f prime at 7 will give me the slope. So this is a very powerful function that we're about to find. It's called the derivative. Now the derivative of a function is defined as follows. We make a small change to notation. We return to that concept of having a secant line. Connect the dots. This is a line you don't need calculus for. We would know these two locations, and we could find the rise over run. But again, the true interest lies here at the tangent slope. So here it is, the elusive tangent slope, balanced up on just one point like that. Now, how do we get there again? Well, we actually identify this. Instead of calling this c, let's just call it x. And over across here, instead of calling this f of c, let's just call it f of x. This is our x value. And how far away do we go from our x value to get our second point? We go delta x distance away. And so this would be x plus delta x. And if you're going to do a function evaluation, you simply look at your current x location. Now, ultimately, the slope of the secant line, while it's interesting, is not what we're truly looking for. We're looking for the slope of the tangent line. And if you remember, we keep reeling this point closer and closer and closer, watching that secant slope lean over. Let me at least put this one in right here. So we'll connect at least these two dots, just to demonstrate to you that what's going on here is the slope of the secant line is literally leaning over and trying to get to the tangent slope. So, the slope of the tangent line at this particular x value should be the limit as delta x approaches 0, that's us pulling the point closer and closer, of the rise over run formula, or the slope of the secant line. Here's my top y value minus my bottom y value. Here's my top x value, or rightmost, minus my leftmost. I mean, we've done this before, only we've used a c. That's really the only change. Now you know how important it is to wait and be patient with delta x going to 0. If you do it too soon, you're going to get 0 over 0, which is neither the derivative nor the slope of any tangent line. But instead of plugging a specific value of c, like c equals 2 or something in here, we're going to leave x alone. In other words, for any value of c, for any value of x. What's going to happen over here is you're not going to get a numerical result anymore. You're going to get a function of x. The name of that function is f prime. We call this the derivative. Now the derivative has a job to do. The derivative will reveal the slope of the tangent line at any value of x. You can imagine the power of having such a function. Once you have it, you don't have to do any more calculus. You want the slope of the tangent line, use this new function. and it'll be an algebraic function in this case. I'm going to start with an algebraic function. In fact, let's start with the parabola, which is x squared. So that's our first function. F of x is our parabola, x squared. We've worked with this particular function before, and we found some slopes of tangent lines, and they matched what we saw on the graph. But let's find this new function called f prime. F prime would be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. This formula is the same for really for any function. We would use that same formula. This is the limit method of finding the derivative. As before, you need to be good at your function evaluation. Wherever you see an x, we've replaced it with x plus delta x. So over here, same thing. We replace it with x plus delta x. I want you to continue to copy the limit over and over until we actually execute the limit, until we actually send delta x to 0, but that doesn't happen until the very end of the problem. So running the function on x plus delta x, this is a squaring function. It simply squares input. F of x, well, right there is x squared. We square input. And you want to spell this all out by squaring it. The binomial. Let's see what we get when we square that binomial. We get x squared. So the shortcut for squaring a binomial, you get x squared. You also get delta x squared. I'll put that over here. But the big question is, what is the middle term that goes in here? And that's all three of these multiplied together. So 2x delta x. 2x and a delta x goes there. This says minus x squared. And it's all over delta x. Keep track of your algebra in this situation. I did say in the previous video, you will always seem to notice some cancellation arithmetically. Once you've canceled those out, you might also notice a common factor of a delta x. There's one here, and there's certainly at least one there. So bring the delta x out front, and you get 2x, because you pulled the delta x out front. This leaves one delta x behind, and look what we found. Seems to happen almost every time, and that is you find a common factor. In fact, we call this the offending factor because that's the very reason why we keep getting 0 over 0. And the moment you eliminate that problem of getting 0 over 0. So what do we get left here? Now you can use direct substitution. By substituting delta x equals 0, we get 2x plus 0. We get 2x. This is referred to as the first derivative, f prime. It is the derivative of f of x. You'll notice it's a very different function. This is a linear function, and that's a quadratic function. But let's see if it does its job. So now, no more limits, no more calculus. We can simply get the slopes of tangent lines using the derivative. So if I draw my parabola right here at the vertex is 0. Let's start right here at x equals 0. Let's draw a tangent line. I think we've seen this one before. There's my tangent line bolded up. And at x equals 0, pretty clear by looking at this graph that the tangent slope should be 0. That's the job of the derivative. Simply tell the derivative where you are, and it should tell you the slope of the tangent line. And that's certainly a match. Let's go elsewhere on this curve. 1, 2. Let's reach up here to x equals 2. And let's draw a tangent line to the curve. Should just touch the curve and be balanced up pretty well on that curve, but only at one point. There it is. There's my tangent slope, or tangent line. So let's pull this one aside. You want the slope of the tangent line. At x equals 2, let's go right to that first derivative, f prime, and plug in where we are at 2. So that's 2x up here. That's 2 times 2. The slope is positive 4. And doesn't that look like a positive slope? So the slope is positive 4. One more. This is great because now that I have the derivative, I can go anywhere I want on this curve. Let's go way back here, -1, -2, -3, which reaches way up here, and it's a very negative slope here. One thing I noticed right away, it's a negative slope. It's a fairly steep slope. Where are we? -1, -2, -3. So the slope of the tangent line should be f prime evaluated at -3. And let's see if that makes any sense. F prime, remember, is our function. It's our derivative now. It's 2x. And the slope comes out to be -6. So it does make sense. The derivative reveals some valuable and important information about our curve, and that is it tells us the slope of the tangent line, and we don't have to keep repeating the limit process. You just need to do it once. So replace c with x, run the limit process, leaving the x alone, get the delta x's to cancel correctly, and it will leave you with the derivative. Oh, we got to put delta x equaling 0 at the end and get rid of all the delta x's. And you will have the first derivative, which tells us the slopes of tangent lines. So it's a pretty valuable function to have. Now, it depends on your curve, of course, as to what your derivative will be. Let's try another one. I would like to discover the derivative for this function. Now, instead of x, it's t. We can have different independent variables, so we're going to call this t, let's say, for time. And let's do the 1 over t curve, or t to the -1. Now, just to give you an image of what that curve looks like, 1 over t or 1 over x would look something like this. So it's got both a horizontal and a vertical asymptote. So that's kind of what that curve should look like. And if I go right here to x equals 1, I have a sneaky suspicion on the slope of that tangent line. My initial thought on the matter is that the slope of that tangent line is actually -1. I know it's a negative slope, but I'm going to say that it's -1, that if we slide that into the origin, it would make a 45-degree angle in quadrants 2 and 4. Let's go over here to another location. That's going to be x equaling -1, and let's draw another tangent line right there. And isn't that interesting? I have the same suspicion on that line, that the slope visually looks negative, and I believe it's going to be -1. So I want to corroborate that with by actually finding the derivative. And once we've found the derivative, I'm going to plug in t equals 1. I'm going to plug in t equals -1. And it shouldn't matter. In both cases, I'm hoping we're going to come up with a slope of -1. So how do you find the derivative? F prime. It's a limit process. It's the limit as, well, maybe in this case delta t goes to 0, because instead of our independent variable x, it's t. And we're going to put here the f of what used to be x plus delta x. I'll put t plus delta t minus the f of t all over delta t. The whole world changed to t's on us because t is the new independent variable. We've got to be extra careful, guys. We need to be good function evaluators. This is the limit as delta t goes to 0. Now, my function is a reciprocal function, so I'm going to get input, and I'm going to get 1 over that input. I'm going to get input, goes in, I get 1 over that input. Boy, don't set delta t to 0 now. Read what you have. You would get 0 over 0. And therefore, the derivative would scream out Basically, the slopes of all tangent lines are undefined, but that's not true. You can see that we've got a couple on the page already. So I'm hoping to get a function back out of this, a real function that gives us some answers. Well, how do you join two fractions together? Think about it. The LCD. So I'm going to use this denominator, and I'm going to multiply the top and bottom by my t here. I'm going to multiply the top and bottom by t plus delta t here. That way, you notice that they now share the same denominator. That's a good sign. So what do we got up there? Well, up top here I have the letter t minus, now distribute through, you get a t, distribute through, and you get a minus delta t. That's what I see up there. T minus delta t. Well, there's my arithmetic cancellation pretty quickly. But what's down below, don't forget you have the denominator, which is a t times t plus delta t. That is the common denominator between the two. Oh, and there's one more denominator, and that's delta t. So let's continue. Oh, what's on top? Minus delta t. What's on the bottom? When you keep dividing by things, they all end up in the denominator, actually. They all kind of pile up into one big denominator when you just keep dividing by items like that. Well, luckily for us, we have found the offending factor. Here it is, guys. The offending factor is canceled out. Remember, you need to copy the limit over and over until you're ready to actually set delta t to 0. And I think we are ready. So go ahead and set delta t to 0, and let's see what we get. Minus 1 doesn't change on top. I get t times t plus 0. I got myself a brand new function. So here's what I've got. The f of t was that 1 over t curve. The new derivative function is minus 1 over t squared. Completely different function. Now, let's remember the job of the derivative function. Its job is to scream out slopes of tangent lines. It says, tell me where you are in either x or t, and I'll tell you the slope of the tangent line. Well, let's talk about where we are. We're right here at t equals 1 or t equals minus 1. And my claim, according to the picture anyway, is the slope, I think, is negative 1. They both look to be the same. What's the tangent slope at t equals 1? In other words, what's the f prime of 1? That's a pretty nice result. What's the tangent slope at t equals negative 1? In other words, what's f prime at negative 1? Well, that's positive 1 down there. Pretty cool stuff. So, this is the magic we're discovering. That is, we can find another function whose job it is to give us the slopes of tangent lines pretty much wherever we would like. Once we have that function, we don't have to do any more calculus. So let's take a look at something else here. I'd like to talk about this notion of differentiability. And I'm going to do so by looking at a curve. Differentiability, what that really means is not your ability to find the derivative, because we just found the derivative. It's whether or not the derivative itself is defined at a particular x or t location in this matter. So you can find the derivative function, put that down, and then if you plug the independent variable in and the derivative comes out undefined, we would say it's not differentiable at that particular location. Let me give you some indications of where that might occur. We just worked on this function. What would you say the slope of the tangent line is at t equals 0? Well, t equals 0 is here. In fact, the f of 0 is undefined. So there's not even a point that I can line the ruler up and try to balance it up. But if I had to say what the slope was, it appears to me, especially since this was based on a limit process, it looks like the slopes of my tangent lines, whether I come at it from the left or the right, I'm looking at some tangent slopes trying to get it to x equals 0, they all seem to be lining up to be vertical. And if it's a vertical slope, I would say that this tangent slope is undefined. Well, we do have a derivative, right? We have this magical function whose job it is to reveal the slopes of tangent lines. So what is the f prime at 0? Undefined, okay? Just as we could see in the picture here. So in this particular example, not only is the y value undefined, the slope is also undefined at that particular location. Now, I want to take a look at a curve with a sharp corner. And a perfect example of that is absolute value. We know that sometimes absolute value spends its life doing nothing and releasing what's inside, basically giving us the x. And sometimes when what's inside is negative, it puts an extra minus sign in front of it. Now that happens when what's inside is positive. This will occur when what's inside was already negative. And so this is really a piecewise defined curve that looks like a V. Because it says when x is greater than 0, use the line y equals x. When x is less than 0, it says use the line y equals minus x. So that's a sharp corner right there. Very sharp corner. The question I would have for you, without really doing the math behind it, I don't think we need to do the limit process to get some of these tangent slopes, right? So here's 1, 2, 3, etc. I would think that the f prime of 3 is the same as the f prime of 2, is the same as the f prime of 1. They're all slope 1 right over there. It's just on a line that has a slope of 1. Now if you go backwards a little bit here, and we look at minus 3, and minus 2, and minus 1, these all have a slope that's negative 1. So all of my tangent slopes behind x equals 0 are all negatively sloped. So here's my problem. What is the slope of the tangent line right here? Now remember where the derivative was born? It was born out of a limit process. So if we zoom in, a limit says we got to be in agreement, whether we come at it from the left or the right. So if I come at it from the left, I keep screaming out slope minus 1, slope minus 1, slope minus 1. So everywhere on my approach from the left side, it feels like I'm headed to slope negative 1. In other words, the slope doesn't even change. So the trend is for the slope to stay negative 1. But if I come at it from this side, I keep getting this signal. Slope equals positive 1 here. Slope equals positive 1 here and here. So as I approach from the right side, I keep getting slope 1, 1, 1. Or if I approach from the left side, I keep getting slope minus 1, minus 1. So what is the slope right here at this location? Remember, the derivative was born from a limit process. Limits have to agree from both sides, and we're not in agreement here. Half of us would say we're approaching slope negative 1. The other half of us might say we're approaching slope positive 1. We are disagreeing right here. So therefore, at that sharp corner, f prime of 0, in fact, is undefined. There is no tangent line there. Even though you could consider balancing it up and making it the x-axis. So you might think that the slope of the tangent line at a sharp corner like that is slope 0. But we have to be in agreement when we come at it from both sides, and we're just not agreeing. We're getting slope -1 on one side, slope +1 on the other side. Okay. So to finish up here, what I'd like to talk about is one more thing about our slope of our tangent line. I've got a very unusual curve for you here, and that's a cube root of x. And something strange happens to the cube root of x curve, and that's this. If you look at it, it kind of comes down here, right down to the origin, lines up for a moment, and then shoots off in that direction. So you can look at slopes here and watch what's happening. You can look at slopes down here, and let's observe what's happening. These slopes, I'm putting little tangent lines to show you that this slope, as you approach from the right side, is getting steeper, steeper, and steeper. Over here, this slope also getting steeper, steeper, and steeper. So at x equals 0, I would say the slope of the tangent line is vertical, but that's infinity, and therefore it's undefined. There are a couple of reasons why the derivative will be undefined, why the slope of the tangent line will be undefined. One thing that might happen is you might get a sharp corner, and you can try this on any graph. Whenever you have a sharp corner, there's very much disagreement between what's going on with slope between the left and the right approaches. You don't get agreement when you get a sharp corner. The derivative evaluated at any sharp corner is undefined. It's not 0. Here's another situation where the derivative is undefined. So I could say f prime at 0, because that is reflective of the slope of the tangent line is 0. At 0 is undefined. And one more thing that might happen here, and that is either your function is undefined like that or like this. Either way. Okay? Here, you can't really balance up your tangent line. So if f of x is undefined, then f prime is also undefined. While you might imagine balancing up a tangent line there is no point really to balance it up on, and therefore your derivative will come out to be undefined. Here, also your function's undefined, and your slope is becoming incredibly steep, and so you can imagine f prime would be infinity or, again, undefined. So if f of x is undefined, then your derivative will become undefined, and we would say that's non-differentiable at these locations. So that brings up an interesting conclusion. Differentiability implies continuity and smoothness. So you can honestly look at a curve and determine if it's differentiable. Is it differentiable at this point? Yes, it's continuous and smooth, and yes, indeed, I can balance up a tangent line. I should be able to calculate that slope. Is it continuous and smooth here? Yes, so there's another tangent line there. Differentiability implies both continuity and smoothness. So, sharp corner. Is the curve differentiable at that sharp corner? No. F prime at C is undefined. The reason is, take a look at these slopes. I'm drawing little tangent lines as I'm getting closer and closer. Little tangent lines as I'm getting closer and closer. And what's happening is these are all positively sloped tangent lines. These are all negatively sloped tangent lines. We're not going to get a match up there. Okay? They're not going to match. So as we approach from one side or the other, we're in disagreement. So it's undefined, meaning it's non-differentiable at x equals c. So therefore, we cannot say that this function is both continuous and smooth. It is continuous, though, but it's not smooth. So differentiability. It's an interesting word. Does not mean you're able to find the derivative function. We should be able to do that. It's when you plug in your x location into the derivative. If it becomes undefined, it's trying to tell you something. It says either the function is undefined at that location, or perhaps the function is continuous, it's just not smooth there. There's a spike or sharp corner there. Differentiability implies continuity and smoothness. That's it for our first derivative. This is the derivative function, which reveals so much useful information. I need you to really get into the homework problems and practice using the limit method. You will find later on that we have other techniques for finding the derivative that are even quicker and easier than the limit method, but we learn using the limit method first. We're going to observe a pattern from the limit method, and then all of a sudden it's going to become a whole lot easier once we know how to do it using calculus. Thanks, everyone.